Thank you. And it's a pleasure to bring greetings from Canada to Professor Posse. He's visited Canada many times, and met him from Winnipeg in the late 90s, I think. And he's always brought a lot of insight to the subject of group rings. And I'd also like to thank the organizers of this meeting. A lot of the topics of this meeting are things that I hold dear to my heart, and really, really happy to have the opportunity to come and speak. And with that, though, I'm not going to talk initially about group rings. I'm going to introduce an area of mathematics that I've been working in where you get to play group ring games with things that are not group rings. And so I'm excited to tell people with expertise in group rings and representation theory about these objects. So the basic idea in algebraic combinatorics is that you have algebraic structures that are coming from combinatorics, that is, counting arrangements and graphs. So when you represent those kinds of things, you use 0-1 matrices. So things are adjacent or related when the entry in the matrix is a 1, where the position corresponds to the things that are being related, and a 0 if they're not related. Now, in this idea, you can create algebras by taking collections of 0-1 matrices. So non-overlapping means that they come from some partition of a set X. The set X has size n, and so the relations are naturally presented as n by n matrices. And if you are fortunate, you get an algebra, which is as big as it can be. So you have a set of 0-1 matrices that should be closed under transpose. Now, this is for semi-simplicity desires. The set of matrices should sum to J, the all ones matrix. And in order to get the identity in your algebra, you want to arrange that. So you say you have a part of the basis, which is a subset of diagonal matrices whose sum is the identity. So the sum of the basis elements will give you the identity, and those are a set of orthogonal idempotents in your algebra that you create. Now, when you do that, you call that a coherent algebra. I'll just abbreviate that by CA. Now, this basis that is in the definition is what we call the standard basis of this coherent algebra. And if you talk to a combinatorialist, you have to say that this is a set of adjacency matrices of a coherent configuration. So that's a certain kind of partition. The size of the set in which you're partitioning is n, so that's what we call the order. And indeed, that does become order for the algebraist. And the dimension of the algebra is the rank. Now, having the set being closed under transpose means that you have a self-adjoint subalgebra of MNC. And from an elementary algebra class in abstract algebra, you can show that that means that your Jacobson radical of this algebra that you get is semi-simple when you use C or R. So you have a semi-simple R or C algebra here. There's a special case which is of interest. The most interesting case is when you only have one element in this delta. In that case, this is exactly the set of adjacency matrices of an association scheme, and you call the algebra an adjacency algebra of the association scheme, or in its initial founding, it was due to Bose and Mesner, and so it's often called the Bose-Mesner algebra of the association scheme. So this is one of the algebras that we're interested in, well, two of the algebras we're interested in, coherent algebras and algebras of association schemes. Now, definitions are always terrible if you don't have examples, so let me give you a few. The way to see these things in a compact format is to write all of the basis elements, since they sum to J and they won't overlap, you can put them all in one package. So you make one n by n matrix where the entries are the labels of the bi in the basis. So the 0 here means that I only have, that B0 here is the identity. So this is the case where the delta is 1. The delta has size 1. So this is an association scheme. I have a few elements, B1, B2, B3, which you'll only see one element in each row and column that have a 1. Okay, so those are representing 3 distinct permutation matrices in this picture. These two here, 4 and 5, B4 and B5, have just 2 1s in every row and column. So where you see a 4, you have to think, well, if you are looking at B4, then that's a 1 in that position. Okay? And you'll see that B4 transpose is also B4 because these reflection positions have the same entry in them. So B4 and B5 are symmetric elements of valency 2. Valency is the number of 1s in every row and column of the EI matrix. B6 transpose is B7, however. Okay? And now when you want to check that this is a coherent algebra or an association scheme, you have to multiply. So if I take B5 and multiply it by B6, I take the 5s in this row, those are position 1s, and I would transpose them across these 2 columns here where the 5s occur. So you think of these 5s lining up with the things in this row. If I'm doing B5 times B6, then I will hit 6s in these 2 spots. And so that means that I will have 1s in these positions. But those positions are, or since I'm getting an algebra, I have to get a linear combination of the B's. And so I must have 2 B2s and 2 B3s as being the answer when I multiply B5 times B6. So that's how the algebra is generated using this basic matrix presentation. This is an association scheme because it has zeros in it. This is a coherent algebra, where the basis is a coherent configuration. And this time we have 2 elements in delta, B0 and B6. We have, and when you have that, then the matrix is separated into blocks. So you have the 1-1 block, the 2-1 block. Those are all separate. So in a coherent configuration, those will be non-overlapping BIs. And then the blocks on the diagonal are actually association scheme subalgebras of the coherent algebra. Here you have valencies, which are common to the rows and columns when you have an element of one of the association schemes, but they can differ when the elements are in these off-diagonal blocks. Still, the order is just the sum of the valencies. That's natural. Now, you might say, well, okay, got an algebra, it's semi-simple. Why should it be interesting to someone in group rings? Well, first of all, group rings are subrings of the adjacency algebras of association schemes. In fact, they are adjacency algebras. So here's the regular representation of our favorite group Q8, quaternion group. And you do that, you get a non-overlapping set of 0, 1 matrices, and the valency of every element is 1. So in that case, you call it a thin association scheme. So groups are just thin association schemes. And group algebras are adjacency algebra of that kind of an association scheme. You can go, there's a lot more than just groups, though. Combinatorials generate a lot of these algebras, and quite interesting ones, using families of graphs. So let me just quickly go through some of these. The complete graph, complete loopless ordinary graph, gives you 2 elements in an association scheme, the identity and the J minus I matrix, so where only the zeros are on the diagonal and 1's everywhere else. That's a unique rank 2 association scheme. Strongly regular graphs, If the A is the adjacency matrix of a strongly regular graph, it will have a graph complement, whose adjacency matrix here I have is AC, and then the identity. And being strongly regular is exactly the condition that this is a three-dimensional algebra. Generates a three-dimensional algebra. And you generalize that to distance regular graphs on n vertices, the distance matrices of the graphs produce symmetric association scheme where every element here is the symmetric matrix, and it will have order n and rank d plus 1, where d is the diameter of the graph. Okay, doubly regular tournaments are the case where you have an asymmetric A and A transpose pair whose sum is j minus I. Those only exist when n is 4u plus 3 for some non-negative u. Okay, but all these are cases of association schemes. Give us algebras. Now, there's an article in 59 by Schneider, which you can use to show that adjacency algebras of association schemes are actually subrings of group rings. So let's see how this works. You take your set of adjacency matrices of an association scheme of order n. Then by your valency condition, each of these non-identity BIs is a matrix where it has exactly the same number of ones in every row and column. And that makes it an extreme element in the convex hull of the permutation matrices. And that's because it's doubly stochastic. And what Schneider proves is that in that case, it has to be a convex combination of these extreme elements, and it will have to have 0 and 1 coefficients. So you get a sum of permutation matrices that doesn't overlap. For each element BI, you have a set of permutation matrices whose sum is that. And those collections all sum to J. That means that your ZS, the ring generated by your basis, is a subring of ZG, where G is the group generated by these derangements. Now, you have to be a little bit careful about this because the derangements are in their permutation matrix representation, so that's the Coxeter representation of Sn. So it's hard to dig these out from just the group ring representation of Sn. But it's there. Special subrings of ZSN that we're actually talking about. Case of association scheme. Now, the algebraic condition it comes from the fact that it's a basis, so that Bi times Bj is some linear combination of these decays, can be isolated in this statement here. You take the structure constants, call them lambda ijk, then the fact that B0 will only occur when you multiply Bi times Bi transpose is captured with this structure constant condition. This extra condition that the structure constant be positive is a little bit extra, but happens for our association schemes and coherent configurations. And we call it the pseudo-inverse condition, so that's what this is called. Now, if you forget that you have a set of 0, 1 matrices and generate the algebra just with a basis B is subject to the condition that it's closed under some involution and satisfies this pseudo-inverse condition and is associative, then you call that a table algebra. And if you renormalize the basis in the right way, it agrees with the definition of what's called a fusion rule algebra, or a fusion ring. So this pseudo-inverse condition is capturing just that, but that's more general, as it turns out, than just being the adjacency algebra and association scheme. I can also generalize this, and it has been done put to good use by Lustig. You can generalize the coherent algebra definition, forget about it being from a basis of 0, 1 matrices, and you get an algebra from taking a unitary subring of MNC and decomposing the identity with a set of orthogonal idempotents and seeing what happens to the basis. So that's called a base string. in Lustig's terminology. Exactly the same idea. Now, the great thing about looking at these things now is that it's almost completely wide open for people in computational, people with computational skill. Coherent configurations are only classified up to order 13 because partitions are hard to manage, and so you don't get very far with a computer at all. This Zivav is a student of Misha Klin in Israel. Naki and Miyamoto looked at classifying association schemes. They got as far as order 30. Order 31 is obstructed because of the non-existence of a classification of Skew-Hadamard matrices, which just occurred a few weeks ago. So there's 3,331 doubly regular tournaments of order 31. So I was making the slides, that wasn't known, but it is now. So this is now up to 35, where we have problems. For association schemes, there are some results that there are some character table constructions that get in the way. So non-commutative rank 5 association schemes don't exist because of some integrality considerations of the character table. Rank 5 table algebras, however, do. So with a few of my co-authors, we looked at that problem and eventually got up to rank 7. There are no non-commutative rank 7 association schemes with 6 asymmetric elements. So those would be like doubly regular tournaments where everything that's not the identity is not its own transpose. But there are table algebras of that kind. For association schemes, there must be at least 2 elements for it to be non-commutative. Symmetric association schemes are commutative. And we don't know if there are some with 4. This is an example of a fairly big problem in algebraic combinatorics, this feasibility problem, or a family of problems, to ask which table algebras are represented by association schemes. Now, it have to be the fact that you have to know that their structure constants are integers. Multiplicities are the normalized row sums in the character table. Those must be positive integers. And graphs have to satisfy the usual regular graph eigenvalue restrictions. There's a lot of things that one can say. Some of these problems are quite famous. So, for example, there's strongly regular graphs whose parameters we can write down, but they're not known to exist. And this is a case where you have just a rank 3 table algebra, and you have to find a 65 by 65 matrix that represents it. I've written some programs that are looking for that kind of thing. Lots of interest in that. And then this is this open case that I just mentioned. They're a non-commutative association scheme of rank 7 with 4 asymmetric elements. So 2 pairs of, they're not equal to their own transpose. So that's not very big. 7 is not very big. Right? So there's lots of room here for people to work. Okay? Now, like all areas of math, there's connection to some fairly deep things. So people started looking at Terwilliger algebras. Terwilliger algebras are a refinement of the coherent algebra definition that is useful in the distance regular graph world. So for these, you have to have the n by n matrix representation. It doesn't work otherwise. So you take your coherent configuration basis. For each, fix one of the points, x, that's being partitioned here. So this x is chosen to be one, say, row of the matrix. For each ai in the basis, you make a diagonal idempotent matrix from that row. You just make it diagonal and put the ones in the position where the ai has ones in that row. going from ones this way, you make them go that way, and then you just generate an algebra over Q. Now it's again, it will be a semi-simple algebra. It's a transpose closed basis, so or a generating set, so it will be semi-simple, and that's this algebra. You can even do this over Z. It's the same construction, okay? And you get an algebra. It'll be a subalgebra, coherent algebra, because these things, your generators all live in a coherent algebra, but it's usually not coherent itself. So it's more interesting. It will depend on X, and you get one of these for each row, but the ones where the rows are being permuted by the automorphism, the combinatorial automorphism group of the scheme, those will be the same. So there's one of these for each orbit of your automorphism group, and that doesn't mean much because some of these association schemes have trivial automorphism group, and so you can get n different Terwilliger algebras from them. Now these are quite important in combinatorics. Give a few little quick examples here. The first one here is the reason why you've never heard of it before, because it's trivial for groups. In association schemes, your Terwilliger algebras are all trivial. But for strongly regular graphs, it's already quite difficult. And what was shown for them is that the characters of the complex Terwilliger algebra, there'll be one of degree 3, which is automatic. So there's always one of the same rank as the S. But this says that all of the others have degree 1 or 2. It's been studied extensively for the distance regular graph people, which leads to all kinds of connections to lovely things. Let me say a little bit about how the first one of these works. For bipartite graphs, what was shown is that there's a mapping from UQSL2 onto TX. So all of the representations of TX are representations of UQSL2. And for many, many distance regular graphs, that same thing gives you a mapping from a nice quantum group onto TX. And so the representations of TX are coming from the quantum group. In places where the quantum group is known to help, then you get a connection between a graph and something that doesn't look to be connected to it whatsoever. This is really quite an interesting thing and quite important in the algebraic combinatorics. But for asymmetric association schemes, we're all the way down to rank 3 and we don't know what's going on. So we were looking at this summer. Student and I, we came up with a few questions. There's an old question of Terwilliger that asks if the integral Terwilliger algebra is sort of naive. There's no other integral matrices in the rational Terwilliger algebra. That seems to be quite fundamental. It's a good question for people who are familiar with generating orders and like that. Okay, that's the definitions of the algebras. One of my goals was to get through those. Now let's get to some theoretical questions. Let's get integral. So you have a ZB as an integral ring. So then you can tensor it with any ring you like and consider representation theory over anything you like. Now, my previous experience was in Schur indices, so I like putting a Q there, but you can put anything you want. It will be semi-simple when a condition like Maschke's theorem holds, and if you go to the poster session tomorrow, one of my students has a poster on that topic. Pitch that a little bit. You can also consider units of ZB. Consider maximal orders between ZB and QB. ZB itself is not a maximal order, but you can find maximal order would be. Zeta functions, I'll say a little bit about that direction. Okay, when you look at this over Q, there's a huge conjecture in the subject about the fields of character values being cyclotomic. So something very strange is happening here because you look at cyclotomic eigenvalues and you look at regular graphs of which every element of an association scheme is the matrix of a regular graph. This fails already at order 9. There's 9 by 9 matrices, regular matrices that don't have cyclotomic eigenvalues. In fact, almost all regular graphs do not have cyclotomic eigenvalues. For table algebras, it already fails at order 13. You can find table algebras that aren't represented by association schemes that have non-cyclotomic eigenvalues. But the conjecture is still open for association schemes. We'll hold for the small things that I defined. Small graphs here, they're easy. Their eigenvalues are easy to write down. On the negative direction, even if you look at association schemes of prime order, there's primes. The smallest one has 4 digits. It's about 6,400 something. Number fields have been shown to exist where those could be the fields of character values for association schemes of prime order that are not cyclotomic. This is an open question even for in the prime world. Possible for it to fail. So there's a table algebra for which it fails, but satisfies all of the conditions, the necessary conditions to be an association scheme. Okay. Now for rational representation theory, we're looking over Q. And so you want to know, what's the Wedderburn decomposition look like? Calculating the Schur indices. So this is the dimension of the division algebras that would occur in a Wedderburn decomposition of each simple component. I'll just standard notation, but the Schur index over Q, I'm just calling M chi. Okay. If the character values are real, then there's a bound which is usually done for groups with the largest root of unity occurring in the character value field, but for here we don't have that because we might not have any. But you still get that rational Schur index is 2 when the field of character values are small. This is a paper of myself with Ranamai Bargi in 2011. Does this. You can talk about the Schur subgroup of the Brouwer group, which is something that study for groups with Angel and Gabriela Piano a few years back. And so question there is, well, if you're bounding the Schur index, it's certainly bounded by the exponent of G in the group world, but we don't know what parameter will bound it in the table algebra or association scheme worlds. And that one can check for. This is a new result that if you only have 2 asymmetric elements, then the rational Schur indices are 1. A lot like US3 in that case. D3. Or I should say. Okay. Modular representation theory. Akihide Anaki is the leader in this direction. So you're representing over a field of characteristic P. Okay. You can make splitting P modular systems. He's shown that if the order is, well, this should be the typo. This should be a prime power. So if order B is P to the n, then it's a local ring. So it's just like it is in groups. One of the big missing parts of the theory is no theory of the defect. 2 candidates for things that Hanaki has generated, but don't know what will play the role of the defect for a block in this context. Partan matrix is symmetric, even though the algebra isn't. So we don't know what restrictions are there on the order theoretic restrictions, I should say, on what kinds of blocks we get. Still, I think that's open for groups too, but this is corresponding question here. Finite representation type, this is done for groups, but not completely done for association schemes. There's one paper by Hirasaka and Hanaki in that direction. Again, quite an open field to dig into. For units, we have result myself and my student Gurmeet Singh. that shows us central torsion units of ZB are trivial. Now, if one follows the path that was blazed by Higman and Berman, we do have the Berman result for this, but we don't know the Higman result even for commutative table algebras. So do we know what the rank of the torsion-free part of the unit group is in terms of this? Now we do have, because of the valency, we do have an augmentation ideal. That was actually something that got me very excited when I started this subject. So because when you have an augmentation ideal, then you can do many things that you can do with groups. And the valency is our augmentation map. So we can ask about normalized torsion units and ask even for a Luther-Passe restriction. There are Luther-Passe method. Conceivable. One of the hang-ups to getting it easily is that we don't have a good notion of conjugacy in these things. There's actually two notions of conjugacy. So you have to figure out which should be the right one for a partial augmentation condition. It tells you something about units. Zeta function. This is the generating function for counting the number of Z modules in a abelian group. And so these are, oh, I guess this isn't set up here. So what I'm, oh yeah, here it is. So ZB, the zeta functions were calculated for small groups by these people, the late 70s, early 80s. The paper by Takahara is quite interesting because the result is so surprisingly complicated. That's why these are differentiated. The Naki and Hirasaka did the complete graph in a few other cases in a 2015 paper, and the prime case. And with Hirasaka and his student Seimin O, he did the case where you take the tensor product of two algebras of any of those types under a locally co-prime condition. This says that primes that ramify in C should not ramify in D, and vice versa. And I didn't write any of the functions down, but the answers are really, they look like zeta functions. They're complicated, reciprocal functions, products thereof. So on. Now, the other thing you'd like to do, the last few minutes here, is you'd like to be able to do algebra. You'd like to have a theory of sub-schemes, quotients, homomorphisms, etc. All of that is laid out by Paul Herman Zishang and Harvey Blau, who worked in this direction a lot. So in order to do sub-association scheme, what you need is just a closed subset. It should be closed under the transpose. And when you multiply two elements of the closed subset, you should get a linear combination of elements in the closed subset. Now, when you do that, you get a partitioning of the row and column sets so that you can reorder so that all of the T-related things are up in your upper left corner. So, and the other things then are partitioned. So you get a partitioning into left cosets, all of which are the same valency. And so your order of T divides your order of S, just like they would in Lagrange's theorem. Your S, the S plus here is just the sum of the elements. The S, so if I look out, write down all of the elements and add them up, I can partition that into double cosets where I'd have the elements that are with non-zero coefficient in the product of T times the single element of S that represents the double coset times T. So that will give me something I can separate from the other things. And those are the elements that give you quotients, actually. This is the major connection to quotients. Okay? Before I get into the quotients, though, there's a question about what's simple in this world. So simple is primitive in this world. If you have no closed subset, then it's simple. Of course, that means in group theory that you would only have the cyclic groups of order P. They're the only groups like that. Now, still true for association schemes that if they have order P, then they are primitive. But there's an important thing missing is that we don't know if there's any primitive non-commutative association scheme. And in this paper with Musachuk and Shu, we found that these rank 5 non-commutative things, which can't be association schemes, are primitive. But we did find also primitive table algebras of rank 6, which might be association schemes. And so we have a candidate which has order 120. Again, it's a table algebra, and we'd like to know, is it an association scheme? And if it is, it's a primitive non-commutative thing. Something like a cyclic group, which isn't commutative. Okay, now back to the double coset idea. If I divide by the order of t, take these double coset characteristic functions, then I get a new basis, which gives me the basis of an association scheme of the reciprocal order. Now for table algebras, that still works, and this doesn't even have to be an integer. The construction still works. Okay, now, when you have a quotient, then you can talk about your association scheme or table algebra homomorphisms. So you'll have just you'll have a kernel. And if you pose maps like this, you get homomorphisms from S to U. Okay? Now, the one major difference here is that every closed subset can be a kernel. Now, if you start with a group and you do its association scheme quotients, you get a certain kind of association scheme called Schurian. Okay? Back to that in a second. Okay. The other direction that people have worked on is direction of extensions. So your direct products are, just like in the group ring world, tensor products of the corresponding group rings. Wreath products are a little bit, it's a bit different than in wreath products of groups, but if you do the permutation wreath product, there's a correspondence that fits in with this model. If you extend by a group that maps into the automorphism group of B, then you can do semi-direct products the same way as you would hope to. Okay. The wreath product generalizes to something called a wedge or circle product. So if you think about what the dimension is, what I'm extending here, when I'm extending, I'm extending from B, but then I get size of C minus 1. So degrees of extensions can be quite arbitrary. One thing to get. Lately, Q has come up with a wedge direct product construction, which is quite general. So the algebra that comes out of this is always what's generated by the kernel of this phi. Phi is an association scheme homomorphisms from B to C. Take its kernel and extend it by C in a direct sum fashion. So this is really quite good. But you notice that I didn't say anything about cohomology. We don't know what the cohomology restrictions for extensions of table algebra should be. No idea. Something that being studied, and wedge direct product is a candidate for a cohomological theorem about extensions of association schemes of table algebra. The other thing you can have is fusions. So in the group ring world, this is the unital Schur ring construction. Okay? And one thing we've noticed is that this star compatibility condition can't be dropped. So to get a fusion, you have to take a partition of B, take characteristic functions on that partition, so just add up elements in each of your partition sets, and get something that is closed under multiplication. Okay? So D squared has to be in ND, and be star compatible. So that when I take star of something in D, I get another thing in D. But we can't drop this. And even for CS3, there is a 4-dimensional subalgebra, which is a fusion subalgebra. Okay? This is a 4-dimensional algebra, which is not semisimple, inside CS3. Have a non-semisimple fusion, but if you fuse this one by putting these together, you get a semisimple semifusion. So the star condition can't be dropped, and we don't really know what it does. Another open direction that comes out of studying this theory. Now there's 3 types of association schemes from the fusion point of view. You have the Schurian association schemes. Those are scheme images of finite groups. There are fusions of those. So these can be unitable, but they're also non-unitable. Okay? Those would be take a quotient and then you fuse. And then you also have these association schemes which are not coming from groups. They are intransitive automorphism groups. They don't fit in these 2 categories. They come directly from coherent configurations, and you fuse so that your delta, you take the elements in delta and you fuse them together and you produce an association scheme from that. And for those, there is no intermediate association scheme fusion. Cyclotomic eigenvalue conjecture, which I'm interested in, holds for first one, and my student Neha has the proof on her poster tomorrow. That topic. But it's open for second and third classes here. So these are fusions of group rings, class 2 there. We don't know if you fuse to get a Schur ring, if it can have a non-cyclotomic character value. That's not known. Could be. I think it's, nobody's done any, where the work on that has been at the current moment is that you have to take a fusion of a non-abelian finite group to produce a Schur ring that may have a non-cyclotomic eigenvalue. That's my last slide, and very much for your attention. Right, so for a zeta function, the Riemann zeta function, there's a product formula. Right? So we generate these zeta functions with formulas, but they take into account the extra structure that comes from the scheme or group. Basically, that's how we approach, right? We get different numerators. What we get. I haven't tried that. Actually, that's one comment I can make is that even for groups, the papers that I've listed here, those are the only papers. So the question you're asking about prime inversion properties of the series that you're producing, get this series, okay? It's coming from reciprocals of 1 times p to the minus s and things like that. And they get the formula and people stop. So it's certainly, I would invite you to look at it. Have some insight, that would be great.